Hello everyone, my name is Youssef and today I'll be talking to you about automatic frustration detection using thermal imaging. During our daily lives, humans interact and have to analyze a lot of social signals. Even for humans, this can be a hard task, let alone robots. So, for example, if we look at the photo on the right there, the person in the middle have a facial expression that a robot or a machine learning algorithm would analyze as sadness, although as humans we can easily tell that this is not the case. That's why in robots we need to use more multimodal systems to understand more about human social signals, especially when it comes to internal states. Internal states are a bit harder to understand as they describe the internal state of the person instead of a visual state. Internal states are important because they help us understand more about humans, and it makes our perception systems more robust. It has been established in the literature that frustration is one of the most common affective states humans go through when interacting with robots. Frustration can cause lower productivity, lower learning efficiency, and slower response time. That's why in this research, we focus more on detecting frustration. A lot of the previous literature discussed how to detect affective states. Affective states like stress and cognitive load, frustration, and disappointment. However, a lot of these use vision or other physiological sensors that can be intrusive or inaccurate. Therefore, in our research, we're going to use thermal imaging instead. Thermal imaging has been discussed a lot in psychology literature, especially when it comes to thermal regions. It has been discussed that each region on our faces can correlate to a different emotion or a different affective state. Hence, in this paper, we've used the similar regions like the forehead, the cheek, the nose, and the lower lip. So our goal is to use thermal imaging to detect frustration, and we're going to do that by comparing the model performances using RGB, facial thermal, and electrodermal activity features. Added to that, we're using a sequential feature selector to understand more about what features can correlate to the best performance of the model. We've decided to collect data from 18 participants aged between 21 and 39 years old. The participants went through two tasks, one cognitive load induced frustration task and the other failure induced frustration task. Between each task, the person was given a NASA TLX questionnaire to know how frustrated the person was. In the cognitive load induced frustration, the person had to program the robot to go from the living room to the hallway using the block diagrams as seen on the figure. This programming task has been adopted from previous works. Added to that, the person was hearing a buzzer. When the buzzer goes off, the person had to change to a mental rotation task and then go back to the main programming task. In the failure-induced frustration task, the person had to play a trivia game that is biased, which the robot would tell the participant that their answer is wrong even though it's completely correct.
Orange. Processing your answer. Please wait. No, that is incorrect. Please try again. Orange.
In our system, we used both RGB and thermal cameras, and they were both calibrated. In addition, we've used electrodermal activities and extracted the tonic and phasic components out of each data point. The full architecture of the system is shown in the figure. The system is ROS-based, which means that the whole pipeline is connected through ROS and synced, and then features are extracted through it. OpenFace was used to extract the landmarks on the facial data, and then correlated with the thermal data to determine the regions due to the landmarks. In addition, each event during the robot interaction was automatically logged through ROS. We've used the k-nearest neighbor model to classify if the person is being frustrated or not. We have 4 models that were trained on thermal RGB and EDA separately and together. In addition, the ground truth data was labeled based on both the cognitive and the failure-induced frustration tasks. In the cognitive load-induced tasks, the whole task was taken as a frustration instance. On the other hand, in the failure-induced task, only when the person answered correctly and the robot replied incorrect 7 seconds afterwards, it was labeled as a frustration instance. Also, we've used the F1 and accuracy as metrics to understand more about the performance of the model. It can be seen here on the figure that the x-axis is the 3 different window sizes that we've used and trained the models on. And on the y-axis, there is the accuracy of the model and the 2 different tasks that we've used, is decog and tfail. It can be seen here if we look at the thermal data that the accuracy peaks on the 7-second window. This means that the changes in the thermal data is a lot slower compared to the RGB data. On the RGB accuracy, it peaks on the 3.5-second window, which means that 1 second is too little data and 7 seconds is too much data. So it leads to less accuracy. In conclusion, comparing the thermal and the RGB features, in the 1 second and the 7-second windows, the accuracies are very similar. That means that thermal data can achieve similar accuracies in these windows. We've also used the sequential floating feature selector to select the highly ranked features that would affect the performance of the model. And it can be seen here that the cheek region was completely discarded from the data. Nose, forehead, and lower lip were the main ones that were chosen. For the RGB modality, the action units that were extracted, the main ones were action unit 28, 2, 4, and 7. These action units correlated to affective states that were chosen from the literature. To check the full list of chosen action units, please check our publication. In this work, we've extracted facial thermal regions by calibrating both the RGB and the thermal imaging. We've also compared 3 different modalities by training 3 different models on each modality, the RGB, the thermal, and the EDA modalities. We've also selected the most prominent features by using the sequential feature selector. Our results show that the thermal changes are less drastic than the RGB, as it needed 7 seconds to reach the maximum accuracy. Added to that, the cheek as a thermal region is less relevant for detecting frustration as it was completely discarded by the feature selector, and just using thermal features can reach similar accuracies to just using the RGB features or just action units. In our future work, we're going to focus more on frustration in the wild as it can be very dynamic. Also, we're going to deploy our system using gamified therapy, hence using our systems in healthcare. Both branches will help us explore more about the models that we can use to understand about the temporal aspect of the data, especially when it comes to frustration in the wild. Thank you so much for listening to my video, and let me know if you have any questions in the main session.